Part 284C3M1B7C8E13C9C6D3P38D19D7b9d8. Line 22f1fa19C3M1B7C8E13C9C6D3P38D19D7b9d8. Fermi Mesoscopic Fluctuations 5G Wow Seti. There's the alien radio signal. And this is the Fermi Edge Singularity keyword Mesoscopics research from the WOW data. March 23rd, 2013. Today's the 27th. The keywords were rate of energy, bilinear form, Fermi line, and Fermi Edge Singularity. This led us to the Mesoscopic X-Ray Edge Problem and Mesoscopic Fluctuations. Keyword was from this previous video. Not going to read the numbers. It says Fermi Edge Mesoscopic. Keyword Fermi Edge Singularities to Mesoscopic Fluctuations. Quote diagrams are from Wiki. This is condensed matter physics. It says disordered state, quantum critical, classical critical, ordered state, and QCP, and then P. Phases, phase transition. Mesoscopic physics is a subdiscipline of condensed matter physics, which deals with materials of an intermediate length scale. The scale of such materials can be described as being between the size of a quantity of atoms, such as a molecule, and of materials measuring micrometers. The lower limit can also be defined as being the size of individual atoms. At the micrometer level are bulk materials. Mesoscopic and macroscopic objects have in common that they both contain a large number of atoms, whereas area properties derived from its constituent materials describe macroscopic objects. As they usually obey the laws of classical mechanics, a mesoscopic object, by contrast, is affected by fluctuations around the average and is subject to quantum mechanics. In other words, a macroscopic device, when scaled down to mesosize, starts revealing quantum mechanical properties. For example, at the macroscopic level, the conductance of a wire increases continuously with its diameter. However, at the mesoscopic level, the wire's conductance is quantized. The increases occur in discrete or individual whole steps. During research, mesoscopic devices are constructed, measured, and observed experimentally and theoretically in order to advance an understanding of the physics of insulators, semiconductors, metals, and superconductors. The applied science of mesoscopic physics deals with the potential of building nanodevices. Mesoscopic physics also addresses fundamental practical problems which occur when a macroscopic object is miniaturized, as with the miniaturization of transistors and semiconductors and electronics. The physical properties of materials change as their size approaches the nanoscale, where the percentage of atoms at the surface of the material becomes significant. For bulk materials larger than 1 micrometer, the percentage of atoms at the surface is insignificant in relation to the number of atoms in the entire material. This subdiscipline has dealt primarily with artificial structures of metal or semiconducting material which have been fabricated by the techniques employed for producing microelectronic circuits. There is no rigid definition for mesoscopic physics, but the systems studied are normally in the range of 100 nm, the size of a typical virus, to 1000 nm, the size of a typical bacterium. 100 nanometers is the approximate upper limit for a nanoparticle. Oh, that's going to change. I don't know. I just have a feeling that when we're done with the WOW data, that's going to change. It's going to get smaller. Thus, mesoscopic physics has a close connection to the fields of nanofabrication and nanotechnology. Devices used in nanotechnology are examples of mesoscopic systems. 3 categories of new phenomena in such systems are interference effects, quantum confinement effects, and charging effects. Keyword quantum confinement effects. Quantum confinement effects describe electrons in terms of energy levels, potential valence bands, conduction band, and electron energy band gaps. Electrons in bulk dielectric material larger than 10 nm can be described by energy bands or electron energy levels. Electrons exist at different energy levels or bands. In bulk materials, these energy levels are described as continuous because the difference in energy is negligible. As electrons stabilize at various energy levels, most vibrate in valence bands. below a forbidden energy level named the band gap. This region is an energy range in where no electron state exists. A smaller amount have energy levels above the forbidden gap, and this is the conduction band. The quantum confinement effect can be observed once the diameter of the particle is of the same magnitude as the wavelength of the electron's wave function. When materials are this small, their electron and optical properties deviate substantially from those of bulk materials. As the material is miniaturized towards nanoscale, the confining dimension naturally decreases, but the characteristics are no longer averaged by bulk and hence continuous, but are at the level of quanta and thus discrete. In other words, the energy spectrum becomes discrete, measured as quanta rather than continuous as in bulk materials. As a result, the band gap asserts itself. There is a small and finite separation between energy levels. This situation of discrete energy levels is called quantum confinement. In addition, quantum confinement effects consist of isolated islands of electrons that may be formed at the pattern interface between two different semiconducting materials. The electrons typically are confined to disc-shaped regions termed quantum dots. The confinement of the electrons in these systems changes to their interaction with electromagnetic radiation significantly as noted above. Because the electron energy levels of quantum dots are discrete rather than continuous, the addition or subtraction of just a few atoms to the quantum dot has the effect of altering the boundaries of the band gap. Changing the geometry of the surface of the quantum dot also changes the band gap energy, owing again to the small size of the dot and the effects of quantum confinement. Keyword: interference effects. In the mesoscopic regime, scattering from defects such as impurities induces interference effects which modulate the flow of electrons. The experimental signature of mesoscopic interference effects is the appearance of reproducible fluctuations in physical quantities. For example, the conductance of a given specimen oscillates in an apparently random manner as a function of fluctuations in experimental parameters. However, the same pattern may be retraced if the experimental parameters are cycled back to their original values. In fact, the patterns observed are reproducible over a period of days. Keyword: time-resolved mesoscopic dynamics. Time-resolved experiments in mesoscopic dynamics, the observation and study at nanoscales of condensed phase dynamics, such as crack formation in solids, phase separation, and rapid fluctuations in the liquid state, or in biologically relevant environments, in the observation and study at nanoscales of the ultrafast dynamics of non-crystalline materials. See also microscopy, nanotechnology, nanomaterials, nanocomposite, and quantum optics. Keyword: quantum optics. I'm going to look at it in the next video. Thanks for watching.